interested in summarizing sets of random variables and comparing pairs of random variables. A statistic of a random variable is a deterministic function of that random variable. The summary statistics of a distribution provide one useful view of how a random variable behaves, and as the name suggests, provides numbers that summarize and characterize the distribution. We describe the mean and the variance, two well-known summary statistics in this video. Mean and covariance are often useful to describe properties of probability distributions, such as expected values and spread. The concept of the expected value is central to machine learning, and the foundational components of probability itself can be derived from the expected value. The expected value of a function g from R to R of a univariate continuous random variable x with distribution p of x is given by e of g of x equals the integral over psi g of x p of x dx. Correspondingly, the expected value of a function g of a discrete random variable x with distribution p of x is given by e of g of x equals the sum all x in psi g of x p of x, where psi is the set of possible outcomes of a random variable x. We consider multivariate random variables x as a finite vector of univariate random variables x1 through xd. For multivariate random variables, we define the expected value element-wise. That is, the expected value of g of x is equal to the expected value under x1 of g of x1 all the way to the expected value under xd of g of xd. And this is in d dimensions. Here the subscript e sub x sub d indicates that we're talking about the expected value with respect to the dth element of the vector x. Definition of the mean is a special case of the expected value, obtained by choosing g to be the identity function. The mean of a random variable x with states x in Rd is an average and is defined as e of x equals e of x1, e of x2, all the way up to e of xd, and that's in d dimensions. For the expected value of xd is the integral over psi of xd p of xd dxd, if x is a continuous random variable, and the sum over all xi in psi x sub I p of xd equals xi, if x is a discrete random variable. For d, and this works for all d between 1 and capital D, the subscript d here indicates the corresponding dimension of x. In one dimension, there are two other intuitive notions of average: median and mode. The median is the middle value if we sort the values, i.e. 50% of the values are greater than the median and 50% are smaller than the median. This idea can be generalized to continuous values by considering the value where the CDF is 0.5. For distributions which are asymmetric or have long tails, the median provides an estimate of a typical value that's closer to human intuition than the mean value. Furthermore, the median is more robust to outliers than the mean. The generalization of the median to higher dimensions is non-trivial, as there's no obvious way to sort when we have more than one dimension. The mode is the most frequently occurring value. For a discrete random variable, the mode is defined as the value of x having the highest frequency of occurrence. For a continuous random variable, the mode is defined as a peak in the density p of x. A particular density p of x may have more than one mode, and furthermore, there may be a very large number of modes in high dimensional distributions. Therefore, finding all modes of a distribution can be computationally challenging. Example, Be a bit tricky, but we'll try and walk through it. We consider a probability distribution given by P of X equals 0.4 times a bunch of normally distributed data around the point 10, around the vector 10, 2, with standard deviation 1001. So it's fairly tidy. I'm going to take 0.6 as well of data that's normally distributed, centered at 0, 0, with standard deviation that's a bit less symmetric. What I've gone ahead and done is I've created a plot for this. What we see here is the marginal distributions in each dimension. So one of the dimensions, the x dimension, is bimodal. We've got a peak here and another peak here. One on the y dimension is unimodal. We've got a peak here and nothing else. Horizontal bimodal univariate distribution illustrates that the mean and median can be different from each other. So in this case, the mean is right here, the median is right here. Well, it's tempting to define the two-dimensional median to be the concatenation of the two medians. Mention the fact that we cannot define an ordering of two-dimensional points makes it difficult. We can't really say where the two-dimensional median is. Well, for each distribution, we're able to talk about the median here or the median here. That's not true for the mean and the mode, right? We've got a mode here, in the middle, here. This is the mode corresponding to 0, 0. This is the mode corresponding to 210. Okay? And here is the median, or sorry, the mean of those two sets of random numbers. For example, we'll let f of x be a piecewise defined function, 2/9 times x minus 1 if x is on the interval 1, 4, and 0 otherwise. We want to find the expected value of f. There's actually two things that we need to do here. First, we need to check that f is really a probability density function. And the second is we have to find the expected value. So is this a PDF? Well, all it needs to be is positive. On 1, 4, it certainly is positive. And the integral over the whole real line has to be 1. So let's check that. So the integral from negative infinity to infinity of f of x dx is equal to the integral from 1 to 4 of 2 over 9 x minus 1 dx, because f is 0 everywhere else. Taking antiderivatives, we get 1/9 x squared minus 2/9 x evaluated from 1 to 4. Simplifying, we get that it's equal to 1. So indeed, this is probability density function. Now, what about the expected value? The expected value here is equal to the integral from negative infinity to infinity x times f of x. So that's just our definition. Now remember that f is 0 other than on the interval 1, 4. So this integral is actually the integral from 1 to 4 of x times f of x, which is, when we simplify, 2 over 9x squared minus 2 over 9x dx. Antiderivatives give us 2 over 27 x cubed minus 1 over 9 x squared. Evaluating that, we get x equals 3. One fact about expected value is that it's a linear operator. Since the expected value of a times a function g plus b times a function h is actually a times the expected value of g plus b times the expected value of h. We use this property in just a second. Covariance intuitively represents the notion of how dependent random variables are to one another. Covariance between two univariate random variables, x and y, in R is given by the expected product of their deviations from their respective means. That is, the covariance of x and y under the random variables capital X, capital Y is equal to the expected value of x minus the expected value of x times y minus the expected value of y. Now, oftentimes, the random variables associated with the expectation or the covariance are clear from the arguments. When this is the case, we're going to start dropping these subscripts. So that is, we're going to drop the y or the xy or the x. We have a theorem here that the covariance of x and y is equal to the expected value of xy minus the expected value of x times the expected value of y. This proof comes from the linearity. So if we let mu x be the expected value of x and mu y be the expected value of y, and those are both real numbers, then the covariance of x and y is equal to the expected value of x minus mu x times y minus mu y. That's equal to xy minus mu x times y minus mu y times x plus mu x mu y. Cleaning that up, we can bring out our mu x's anywhere we've got those. So we end up with the expected value of xy minus mu x times the expected value of y minus mu y times the expected value of x minus mu x mu y. That comes from the linearity property. Now again, substituting in mu x equals expected value of x and mu y equals the expected value of y, we get here then that the expected value of xy, this is equal to the expected value of xy minus the expected value of x times the expected value of y. Here's another example. Grades in a class are given in the following table. Compute the covariance between the assignments and the tests. Okay, so the first thing we want to do is find the expected value of the assignments and the expected value of the tests. The expected value of the assignments are the sum of the values times the probability of each value. So probability of 50 is a quarter, probability of 60 is a quarter, probability of 70 is a quarter, probability of 80 is a quarter. Add all that up, we get 65. Same thing with the expected value of the test. The expected value for the test is 68.75. We want to find x minus the expected value of the assignments. So I take my assignment value, my 50, and I subtract off my expected value, 65, and I come up with minus 15. And I do that for every one of the assignments. Similarly, I want to do that for all of my tests. So I can go ahead and do that for all of my tests, bearing in mind that the expected value of the test is 68.75, not 65. Next, since the expected value, the covariance is the expected value of the product of x minus the expected value times y minus the expected value, I'll calculate x minus the expected value of x times y minus the expected value of y. So I'm simply multiplying the value in this column by the value in this column, and I come up with my products. Now my covariance formula is just the sum of the products of x minus the expected value of x times y minus the expected value of y times the probability associated with each one. So 206.25 times a quarter plus 18.75 times a quarter, 6.25 times a quarter, 243.75 times a quarter, or 118.75. That's my covariance in this example. Covariance of a variable with itself is called the variance. And we denote that by v of x. So v of x is the covariance of x with itself, which of course we know as the expected value of x minus the expected value of x squared, or the expected value of x squared minus the square of the expected value of x. If we take the square root of the variance, we get what's called the standard deviation. That's often denoted by sigma. Here's another example. Assignment grades are given in the table. Compute the variance. We've already figured out that the expected value of these assignment grades are going to be 65. Again, we're just using the formula expected value of x is equal to the sum of all the x's times the p of x's. We can also compute the square of these x's, which gives us the expected value of the assignment score squared equal to the sum of x squared times p of x. So when we add all that up, 2,500 times a quarter, 3,600 times a quarter, 4,900 times a quarter, 6,400 times a quarter, we get 4,350. Keeping in mind our expected value of the assignment and our expected value of the assignment squared, we can compute our variance. Our variance here is the expected value of the assignment squared minus the square of the expected value of the assignment. So in this case, 4,350 minus 65 squared, or 125. We've got the variance. We may as well find the standard deviation by taking the positive square root, which is 11.18. Covariance can be generalized to multivariate random variables. Two random variables, x and y, with states x in Rd and y in Re, respectively. The covariance between x and y is defined as covariance of x and y equals the expected value of xy transpose minus the expected value of x times the expected value of y transpose, which is equal to the covariance of yx transpose. This definition can be applied with the same multivariate random variable in both arguments, which results in useful concept that intuitively captures the spread of the random variable. For a multivariate random variable, the variance describes the relation between individual dimensions of the random variable. The variance of a random variable x with states x in Rd and a mean vector mu in Rd is defined as Vx equals the covariance of x and x, which is equal to the expected value of x minus mu times x minus mu transpose, which is equal to the expected value of x transpose minus the expected value of x times the expected value of x transpose, or a matrix consisting of the covariance pairings for each pair of xi and xj. This d by d matrix is called the covariance matrix of the multivariate random variable x. We want to compare the covariance between different pairs of random variables. It turns out that the variance of each random variable affects the value of the covariance. The normalized version of the covariance is called the correlation. Correlation between two random variables, x and y, is given by core of x and y equals covariance of x and y over the square root of the product of the variance of x times variance of y. That's normalized to be between -1 and 1. The correlation matrix is the covariance matrix of standardized random variables x over sigma x. In other words, each random variable is divided by its standard deviation, the square root of the variance, in the correlation matrix. The covariance and correlation indicate how two random variables are related. Positive correlation means that as x grows, y also grows. Negative correlation means that as x increases, then y decreases. Grades in a class are given in the following table. Compute their correlation. We've already done most of this. And in fact, we know that the covariance is 118.75. The variance in x is 125. The variance in y we can calculate to be 117.1875. Therefore, the correlation is the covariance divided by the variance of x times variance 2, the square root of that. So we get the square root of 125 times 117.1875 under the square root. 118.75 divided by that number, which turns out to be 98.12. In our next video, we'll continue to explore means and covariances.